Okay, friends. So you just watched a game of Egg Russian Roulette, or Russian Egg Roulette, or whatever it's called, with Jimmy Fallon and Peyton Manning and Magic Johnson. It's a great little game because it's a perfect example of a probability experiment where you know enough about it to generally understand the outcomes, but there's still an element of randomness and surprise to it, i.e. where the raw eggs are. So you know that there's 4 raw eggs in that carton, and you're trying to avoid them, but there's an element of randomness because you can't identify the raw eggs. All the eggs look the same. I love this game. I don't know where Jimmy got it from. I did read that there was a school in Maryland whose principal and vice principal played the game to encourage a fundraiser that their school was having, and Jimmy found out about it and matched the fundraising goal. I'm not sure if he got the idea then or they got the idea from him or whatever. It doesn't really matter. What matters is it's probability. The probability of the person who's going first, Peyton Manning in this chain. So imagine you are sitting where Peyton sits. You get to draw the first egg. I want you to hit pause here in a second and scratch down your guess as to what is the probability or chance or likelihood of getting a raw egg. Give it a shot. Okay, hopefully you wrote down some kind of a number. Maybe you wrote down, I have no idea. Now that you've got that, I want you to hit pause again and answer, what's the chance of getting a hard-boiled egg? Okay, so now you have 2 numbers. You wrote down the chance of getting a raw egg if you went first, and the chance of getting a hard-boiled egg if you went first. So those are obviously, they're called mutually exclusive outcomes. You can't get an egg and have it both be raw and hard-boiled. It's either one or the other, and it's gotta be one of them. So I've asked this question to a number of students over the years and gotten all kinds of answers. One of the answers I get is, well, it's either raw or it's hard-boiled, so it's 50-50. 50-50 is a very important probability for me personally, because when I have no idea about how likely something is, I always start at 50-50 and then refine it as I go. But some of you might hear somebody say it's 50-50 and you might say, no, it can't be 50-50. There are more raw eggs, there are more hard-boiled eggs than raw eggs. So you must be twice as likely to get a hard-boiled egg as a raw one, which also makes sense. So we've got kind of 2 schools of thought now. You got the 50-50, it's either raw or it's hard-boiled. Somebody might say, no, that can't be right. 50-50 implies equality of outcomes. The hard-boiled case must be twice as likely as the raw case. And then somebody else might swoop in and go, well, there's 12 eggs, and 8 of them are hard-boiled. Therefore, there's an 8 in 12 chance that the egg is going to be hard-boiled. And by the same kind of math, there's a 4 in 12 chance that the egg will be raw. And the kind of the good news is that there's truth to all 3 of those statements. All 3 of those statements have parts, at least parts, that are 100% correct. And I want to kind of focus in later videos on the pieces that are correct, but I want to ask right now, going into the next video, what would it mean? Let's suppose the 8 in 12 chance of getting a hard-boiled egg is correct, and therefore the 4 in 12 chance is also correct. What would that mean? What meaning does it have to have an 8 in 12 chance? Let's take a look.